Okay, so I think that started the recording, hopefully. Right, so everyone, welcome to this week's first GROOT talk. Today we'll be hearing from Bridget Schreiner from the University of Notre Dame, who will be telling us about secondary homological and representation stability.
Great, thank you so much for giving me the opportunity to speak. So my work focuses mostly on stability and finding connections to calculus of functors, but talking about stability and calculus of functors in the same talk is kind of a lot of background to get through. So today we're going to focus on stability. So first I'm going to talk some about primary stability, both homological stability and representation stability, because I really like to highlight kind of the connection between the two. And then I'm going to talk about two examples of secondary stability. So the first one is homological stability of mapping class groups, and the second is representation stability of ordered configuration spaces. So when I was first learning about secondary stability, I liked having both of these examples instead of just focusing on one, because in my opinion, the statement of secondary stability for mapping class groups is easier to understand. But the map that induces secondary stability for ordered configuration spaces is easier. So if you have both of these examples, you can kind of understand both the statement of secondary stability and where these maps come from and kind of put them together. And then at the end, if I have time, I'll talk about kind of the similarities between the two examples and how they indicate a general approach, as well as kind of the difficulties of following this approach in general. And if I have extra time, then maybe tie a little bit of my own work in, but we'll see. Feel free to stop me at any point if you have questions. So in both of these cases, we'll be studying a sequence of mathematical objects. So for homological stability, we say that a sequence of groups or spaces G1, G2, Gn, with maps between them, satisfies homological stability. If the homology eventually stabilizes. So what this means is the induced maps Hi, Gn, Hi, Gn plus 1 is an isomorphism once n gets sufficiently large. And here n can depend on I, so for each I, we'll have some threshold past which this homology stabilizes. And I like to think of this as our groups or spaces are getting kind of similar enough to each other as we go to infinity. Just like with a sequence of numbers, we have convergence if the numbers get similar enough as we go to infinity. So we have a lot of examples of this. A lot of well-known groups do satisfy this. So the symmetric groups, for example. This example is due to Nikoka. And we have the sequence of symmetric groups just by inclusion. And this sequence satisfies homological stability. For n greater than or equal to 2i. Another kind of common example is the general linear groups. And this, I believe, is due to Quillen. So we have F, a field, not equal to F2. And we can consider the maps from GL and F to GL n plus 1 F by taking a matrix A to the matrix where we've just added a 1 in the lower right-hand corner. And this satisfies homological stability. For n greater than or equal to I plus 1. Now, one of the examples we'll be looking at in more detail later is that of mapping class groups. And this is due to a lot of people. So I'll put Harrer, Boldson, and then a ... because there's a lot of different ways to consider this. The particular stabilization we'll be considering is just one of them. There are a lot of different kind of stability maps here. But for here, we'll let SG1 be a genus G surface with one boundary component. And then I'll denote by gamma G1 its mapping class group. And just to make sure we're all on the same page, this here will mean pi naught of the diffeomorphism group of SG1 rel the boundary. We have a map that takes SG1 to SG plus 1, 1, just by kind of gluing on an extra piece. So if our SG1 looks like this, then we kind of just glue on an extra chunk and get a genus G plus 1 surface where we've glued this on. And this induces a map from the mapping class group of the surface with genus G to the next mapping class group. And this is the stabilization map we'll be using here. And here we have homological stability. Once G is greater than or equal to 3i plus 4 over 2. So the reason I say there are lots more ways to do this example, you can consider more than one boundary component. You can consider stabilization maps which increase the number of boundary components rather than the genus. You can consider maps which increase both the genus and the number of boundary components, etc. There are just lots of ways to kind of play with this example, which is really cool. So we'll come back to this a little later. And our kind of last example here is going to be unordered configuration spaces. And this again is kind of due to a lot of people, but I believe it was originally due to McDuff, and some improvements on the bounds were made by Siegel. So for here, we'll have an open manifold. And we'll consider the unordered configuration space, which I'll denote Bn of M. And this is going to be the set of n tuples of points such that xi is in M and the points are distinct. And then mod out by the action of this metric group, which interchanges the points. So basically, we're just getting rid of the labels. Since M is open, we get a map Bn M to Bn plus 1 M. And here I'm going to be a little imprecise about what I mean, but I'll draw a picture later. But by adding a point near infinity, and this gives a sequence that satisfies homological stability. And I'm actually going to be non-specific about the range here because it depends on the dimension of your manifold and some other things. But it does eventually satisfy homological stability. Now, an obvious question is, what about ordered configuration spaces? And it turns out that ordered configuration spaces do not satisfy homological stability for any value of n or I. And it's kind of for what I call a silly reason, which is when we include the nth space into the n plus first, we have this extra label for a point floating around the n plus first. And so you're never going to get an isomorphism on homology just because that kind of extra label is never going to be included. Even if the classes are somehow the same shape, we still have that extra label that's never going to be hit. And so that's where representation stability kind of comes in. And it allows us to look at this as a representation of the symmetric group and kind of mix that extra label in. So I'll make that a little more precise. So here we'll still be considering a sequence, but this time we'll have a little extra structure. So we'll be looking at a sequence of sigma n representations, by which I mean just a vector space with a sigma n action. So we'll have V1, V2, sorry. We'll have maps between them that I do want to name here. So I'll call them V1, V2, etc. And then the nth thing has an action of sigma n. And then we have some conditions like these phi maps should be equivariant. And basically this should just be a nice enough sequence. The things you want to be true should be true. And we say that this satisfies representation stability if So there are a number of definitions of this. I'm going to give a slightly imprecise one here, just to simplify things. But if Vn is generated as a vector space by the image of the previous thing, so phi n minus 1 of Vn minus 1, and the action of sigma n. So one question I get a lot from people who do algebra is whether this means that Vn is just the induced representation from Vn minus 1. And it turns out not quite, but it is a quotient of that induced representation, if you'd like to think about it that way. So using this, we kind of are taking into account this action of sigma n. And we do get this type of stability for ordered configuration spaces. And this is due to Church, Ellenberg, and Farb. So once again, we'll consider an open manifold. And we'll have maps from the nth ordered configuration space, which I'll denote conf n m, to conf n plus 1 m, by taking a configuration and adding an extra point. So we have 1, 2, up through n. And we need to make sure that point is distinct from any point we had before. So what we do is we use the fact that M is open to insert a copy of Euclidean space kind of out near basically where the boundary would be. You can think about it, but basically just far enough away from the other points. So we'll have 1, 2, up through n, our original n points. And then we have a copy of the Euclidean space. We put a point labeled n plus 1. And that makes sure that this n plus first point isn't the same as any of the previous n's. Of course, this map is up to homotopy. So I should put up to homotopy. But this gives a well-defined map on homology. And so now we can build a sequence like the one we were considering for representation stability. So we have HI of the first configuration space, HI of the second, and the nth symmetric group acts on the nth thing by interchanging the points. And this sequence satisfies representation stability for n greater than or equal to 2i plus 1. So once the number of points is large enough, our homology group is generated by the image of the previous thing, and then kind of interchanging these labels gets us the rest of the homology group. So for secondary stability, it's helpful to kind of rephrase our notions of primary stability. It's slightly easier to rephrase homological stability. So we want to think about things in terms of kind of differences. So here we have homological stability. If the relative homology gn minus 1 is eventually 0. And for representation stability, we want a way to kind of phrase the same thing, that kind of the difference between the nth thing and the n minus first thing is 0. So remember that we're considering a sequence of vector spaces with some symmetric group actions. To rephrase this, it's helpful to look at the category where the objects are finite sets and morphisms are injections. And then consider a functor which I'll call like fancy V, from Fi to some category of modules. Where V of the set of 1 through n is equal to Vn. So this is 1 through n. And then the automorphisms of 1 through n in this category are just sigma n. So that kind of gives us our sigma n action automatically. So we have here representation stability. Sorry. If we take this nth thing and mod out by basically all the possible images of the n minus first thing. So we take the sum over subsets of 1 through n of size n minus 1 and apply our functor to that. And if that's 0, then we have representation stability. So this is basically saying the same thing, just now accounting for that sigma n action. We're just killing off all possible images of that n minus first thing. And we call this the Fi homology of V at n. So if you see that in the literature anywhere, if you're looking at representation stability, it's just this kind of measuring how much of the nth thing is generated by the n minus first thing. And now we have primary stability, both phrased in terms of kind of differences, and secondary stability, we're looking at kind of the differences between these differences. So our first example will be mapping class groups. And this is due to Galatius Kupers, Randall-Williams. So just to recall, we have primary stability, which says that HI of gamma G1 relative to HI of gamma G minus 1 is 0 for G large enough. And we want to know if there's some sort of stability that happens before this. So for a smaller value of G, what can we say about this sequence? So as I was saying at the beginning, secondary stability is kind of easier to phrase in this case. So I'll go ahead and give the statement. So the statement is that there are maps phi star. Now going from the I minus second homology of gamma G minus 3, 1 relative to gamma G minus 4, 1. To this relative homology we were looking at for primary stability. And these are isomorphisms for G greater than I, but less than the primary stability range. So even if this HI of gamma G1 relative to gamma G minus 1, 1 isn't 0, we can kind of account for that difference by this kind of lower difference that's happening in a lower homology group. This is true for both rational and integral coefficients. But here I'll be talking about the map for rational coefficients because it is slightly easier to describe. So for Q coefficients, I believe the range is I less than or equal to 4G minus 6 over 5. And if you actually like plug in some numbers for the primary stability range and secondary stability range, this happens kind of just before the primary stability range. It's not a wide range, but it does give us a bit of information of what's happening in this sequence before that that primary stability range. So still for Q coefficients, I'll look at a bit of the strategy for proof. So much of the strategy is just in constructing this map. So for this, we need a bit of extra structure. And so we'll consider all mapping class groups at once. Which I'll write as gamma bullet 1. So we're just leaving the genus arbitrary for the moment. We construct an E2 algebra structure on this kind of sequence. So that means we have a map from C22 across gamma bullet 1, gamma bullet 1 to itself, where this is the little 2, or I guess the second space of the little 2 cubes operad. And what this structure isn't exactly important for the map that we want. But what it does is it induces a map on homology. So we want to look at the 0th homology of group of C22, tensored with the second homology group of gamma 3,1, and then the I minus second homology group of gamma G minus 3,1. And this maps to the ith homology. So we've just added the degree of the homology group together of gamma G1. So we just added the genuses together there. And now this piece here, the last piece, is kind of looking similar to what we want, except that it's not relative homology yet. But we do have that degree shift that we want and that genus shift that we want. And so to specify a particular map from that group to HI of gamma G1, we need to essentially choose elements in those first 2 homology groups. So here we fix homology classes, which I'll call U0 in H0 of C22. This just winds up being the generator. And we call it lambda in H2 gamma 3,1. And this doesn't have a good description as far as I'm aware, which is why I'm kind of sliding it through a little bit. If you are familiar with cohomology classes, I believe it's the homology analog of the Miller-Morita-Mumford class. But I don't have a good kind of geometric description of what it is. But fixing these classes gives us a map U0 tensor lambda. And I'll say it's an induced map because it's going to be on relative homology. Gamma G minus 3,1, gamma G minus 4,1. To HI of gamma G1, gamma G minus 1, 1. And this is the stabilization map that we want for rational coefficients. So from here, there's just a spectral sequence argument to show that this is eventually an isomorphism. And this, I'll again say, is only for rational coefficients. For integral coefficients, there is also a stabilization map, but this map is never an isomorphism, so we need to make some further choices. And that one is a little harder to describe, so I'm focusing on the rational case here. So this kind of setup is what I see a lot in the secondary stability. We need to introduce extra structure to get these stability maps, these maps of differences between differences. And then there's a spectral sequence argument, which shows we have an isomorphism. Before I move on to the next example, are there any questions? All right. So for the next example, we'll be looking at secondary representation stability. So this is for ordered configuration spaces. And this is due to Miller and Wilson. So first, I'll just remind us what primary stability means here. In our language of finite sets and injections, we're considering the functor that takes a finite set S to configurations of S points in a manifold M, by which I mean points labeled by the elements of S. And I'll also specify here that dimension of M equals 2, just because the classes are a little different for higher dimensions. So we know primary stability says that HI of configurations of n points in M is generated by the image of the n minus first and sigma n action, or in other words, the Fi homology of this functor taking a set to its to the homology of the configuration spaces. So take this functor, evaluate it on n, is eventually 0. Where this again means taking the nth thing and killing off all the images of the n minus first thing. Now, secondary stability says something similar to what we had before, where even if we're not generated by the n minus first thing, we may be able to take generators from some lower homology group and then get everything that way. So roughly, this says there are maps from H I minus 1 of configurations of n minus 2 points in M to configurations of n points in M, the ith homology. Such that HI of configurations of n points in M is generated by 3 things now. So the image of HI of configurations of n minus 1 points in M, HI minus 1 of configurations of n minus 2 points in M, and the sigma n action. The reason I'm kind of stating this imprecisely here is that we need to kind of add more structure before we can even really state the result precisely. But first I'm going to kind of go through the map And then hopefully I'll have time to kind of show you the strategy for proof again here.
So I have a question here. So when you say that it's generated by HI of like the n-1 configurations, that means like under a previous inclusion map, and then the image of the I-1 of homology is under this new map. Is that? Okay.
Yes, exactly. Yeah.
Thanks.
Thank you. Yeah, so it's both images together and then the sigma n action.
Great.
So for our proof, we first need these maps. So like you said, we have that previous inclusion, and now we need these kind of new maps. So here we have a nice geometric description of these maps, where previously we were including one extra point in a copy of Euclidean space in our manifold. And here we're basically doing the same thing. We're just going to add 2 points. Since our manifold is two-dimensional, we have configurations of 2 points in R2. And we're going to configurations of n points in M. And we have kind of the same picture we did before. So we have our open manifold. And n-2 points in it. We have our copy of R2. 2 points in that. And then we stick them together to get our configuration of n points in M. So we have this copy of R2 and just glue our points in there. And this makes sure that none of these points hit each other, because that's kind of the important thing in the configuration space. And this again induces a map on homology. So in particular, we'll be looking at the I-1st homology of configurations of n-2 points, tensor with H1 of configurations of 2 points in R2, and look at the map from there to HI of configurations of n points in M. And now we just need to fix a class in this HI of configurations of 2 points in R2. And so the class we'll fix is going to be the class of the point labeled n-1 and the point n kind of orbiting around it counterclockwise. So this is a map from a circle to the configuration space that gives us a class in the first homology. So I guess I'll call that sigma. And this gives us our secondary stabilization map. So this gives us the map, blank tensor to sigma, from H-1 of configurations of n-2 points in M to HI of configurations of n points in M. And then in order to kind of get what we actually want for secondary stability, right, we want to be able to consider this map and the primary stabilization map at the same time. So we use this to get a map on the Fi homology. So the Fi homology is what we need for primary stability. And then we want to consider this further map for secondary stability. So in order, I guess maybe getting a map isn't quite the right phrasing, but giving this functor that takes n to the Fi homology that we want of H, and I'm going to put I plus n over 2 here of configurations in M evaluated at n. So this way, if I increase the number of points by 2, I increase the degree of homology by 1 because of that over 2. So this is kind of what we want to consider. And we give this, instead of the structure of this functor from Fi to our mod, we have to add some more letters. So I'll write this first and then tell you what it means. So FIM plus module. So a functor from this category, which is finite sets with injections. And in ordered matching on the complement. So basically all we're doing here is we're taking an injection from, in our case, n minus 2 to n, and then we're picking 2 points to be this homology class that we're adding. The reason we need this matching is because we need 2 points, one orbiting the other. And the reason we need it to be ordered is just so we know which one is orbiting and which one is staying still. So this structure is basically just what we need in order to get the secondary stabilization map on homology. And then we have basically the same Fi homology computation we did to show primary stability. We can do a similar thing to show that the FIM plus homology is eventually 0. And I'm not going to write it out because the formula is a little complicated, but it's basically the same thing, where instead of killing off all the images of the n minus first things, we're just killing off all the images of the n minus second things because we've already killed off the n minus first things. And I'm pretty much out of time because I think these are supposed to be 50-minute talks. So I think I'll just briefly say this kind of strategy of adding a little bit of extra structure and then choosing homology classes is kind of difficult in general. A lot of times these choices are non-canonical and we could make other choices. And then also for higher stability, we would need, say, like an E3 algebra structure to get to tertiary homological stability. We would need ordered like 3 tuples of points in our complement to get this higher representation stability. So it seems really difficult to kind of generalize these concepts to higher stability, but it is something that I'm very interested in and looking at right now. And I think I will go ahead and end there.
Right. So let's go ahead and thank Bridget for a wonderful talk. Does anyone have any questions for the speaker?
So in your notation for the Fi homology, I don't know if it would be possible to like say briefly, but is there any significance behind the 0 index that you have? So you denoted it as H sub 0 Fi, and yeah.
Yeah, so I think there are higher kind of Fi homology groups, but I don't know much about them. So I'm giving you kind of a very biased view of representation stability because I'm a topologist. There's really, really deep algebra that goes into these Fi modules that I don't know very much about. So I believe there are other things going on there that unfortunately I just don't have a good answer for.
Thank you.
Oh, I see. So, Eleftheria has a question. Feel free to unmute yourself and ask if you'd like.
Can you hear me?
Yep.
All right. So thanks for the talk. I had a quick question about the argument for the secondary representation stability for order configuration spaces. So for the proof that you do to show that there's no like this works over like Z coefficients, right? There's no restriction over the coefficients like for the case of mapping class groups, or is there?
So I believe that in the paper they do it for Q coefficients only. It does definitely work with Z coefficients for Euclidean space, and you can actually kind of get your hands on those computations quite easily, but I don't know in general. There also, I guess I should say, is no known bound for secondary stability for the ordered configuration spaces, because you show it just by showing that this thing eventually has to be 0, but we don't know where that happens. So I don't know if the coefficients have anything to do with that, or like if it's easier with the rational coefficients. But yeah, so sorry, that was kind of an unclear answer, but it does work in some cases with Z coefficients. I don't know about in general.
Perfect. Thanks.
Kind of a question about what you meant by like higher stability. So I'm wondering, we have this kind of like primary stability, which kind of feels like a first derivative or a first difference or something, and then secondary kind of feels like a second derivative. So are you generalizing kind of in that direction or something totally different?
So kind of both. So I don't know how much you know about calculus, but this whole thing feels very much like a cross effect to me. So I have some like algebraic cross effect that I've constructed that seems to have some indications for stability. And I'm hoping it'll give us a more clear answer as to how to do the higher stability. There are kind of two ways you could go for this, right? Because you have to introduce this structure in kind of a non-canonical way. So either you could try to find a way to make that canonical, or you could try to find a way to do this without having to introduce that higher structure. And I think based on what I've looked at, that both are possible. They just will give you different notions of higher stability. So with the kind of looking at not at having to add an extra structure, I think that's more of a calculus direction. And then looking at a way to make this more canonical, I think there should be some kind of operand structure governing that kind of makes it a little more canonical. So I'm kind of interested in both, but we'll see.
Speaking of like canonical things, I noticed like kind of in both stories here, you had this map that had like it was like a multi-array map that had some inputs, but then you fixed a couple of like special classes to get it to be a just one input. How much like how sensitive are these arguments to those choices, and like are these classes like pretty well understood? Or
so for the homological stability, I know if you fix that particular class, you do not get stability with Z coefficients. So coefficient wise, it's definitely sensitive to that. But there is a way to make it work with Z coefficients. I don't remember how to do it off the top of my head, but it is a very similar argument. You just have to kind of pick a different class, I believe. So they're definitely sensitive with respect to coefficients. I don't know how the ranges change. So yeah, I don't know if you would get a better range if you kind of picked a different map, but that would be an interesting thing to look at.
yeah, any other questions? So maybe let's thank the speaker once more. And I will see if I can stop the recording.